Good morning, my name is Maribel and I'm going to present the results of my PhD entitled Acidification and Transports of Water Masses and CO2 in the North Atlantic. This thesis has been supervised by Dr. Fitz Fernandez Perez. It's not working, okay. So I'm going to start by giving a general introduction about the CO2 cycle and the importance of the North Atlantic in that cycle. Then I'm going to expose the main goals of my PhD and the results of the studies performed to achieve those goals. And then I'm going to expose the main conclusions of those studies. So a small portion of the Earth's atmosphere is composed of greenhouse gases that absorb and contain infrared radiation, which warms the Earth's surface and atmosphere. Since the Industrial Revolution, anthropogenic activities have been gradually increasing the CO2 concentration in the atmosphere. But not all this CO2 has remained in the atmosphere. Part of it has been absorbed by the ocean and land, thus limiting the rise in the concentration of atmospheric CO2 and hence the warming related to this greenhouse gas. When CO2 dissolves in seawater, they react and form carbonic acid, which rapidly dissociates into carbonate ions, which in turn can dissociate into bicarbonate ions, which in turn can dissociate into carbonate ions. But dissociation reaction reduces the pH of seawater. In this plot are represented the relative fractions of the seawater carbon species, and in the pH of the modern surface seawaters there is a relatively high proportion of carbonate ions, which is represented in green. But if the pH of the seawater lowers due to the increase in the concentration of CO2, the concentration of carbonate ions will decrease, and this might affect marine calcifying organisms like Coccolithophora, foraminifera, and corals. Recent studies show that the present uptake of anthropogenic CO2 and the subsequent acidification is about 100 times faster than during the last ice age. And this rate far exceeds the regulation capacity of the Earth system feedbacks to restore the system. Therefore, there is a growing concern about how ocean acidification might impact marine organisms, global biogeochemical cycles, and climate. So to know how much of the anthropogenic CO2 has been uptaken by the ocean, we require a method that allows distinguishing the natural and anthropogenic components. But this is a difficult task for a variety of reasons. First, anthropogenic CO2 cannot be distinguished from natural CO2, and it has to be inferred from indirect means. Second, the anthropogenic perturbation represents only about 3% of the total dissolved inorganic carbon in the ocean. And finally, the anthropogenic CO2 presents a distribution that is rather heterogeneous in the ocean. Therefore, several methodologies have been developed to estimate the anthropogenic concentration in the ocean. Fundamentally, these calculations are approached either using bulk calculation methods or using methods based on the measurements on transient tracers. Bulk calculation methods try to separate the anthropogenic perturbation based on the premise that the anthropogenic CO2 can be isolated from the measured total dissolved inorganic carbon by subtracting the pre-industrial value and the contribution of the biology. Furthermore, a disequilibrium term is also included to account for the fact that the surface seawaters are rarely in complete equilibrium with the CO2 concentration in the atmosphere. Fundamentally, we can the bulk calculation methods are the delta C star and the variations thereof, such as the physicity zero methods. There are other methods of bulk calculation, but these are the main ones. And the main difference between both terms is the treatment of this equilibrium term. And the delta C star method assumes a disequilibrium term that is constant over time, while the physicity zero method takes into account the temporal variability of this term, and assumes a disequilibrium term that is proportional to the concentration of anthropogenic CO2 in the water masses. The transient tracer-based methods determine the age of a water parcel based on the measurements of transient tracers such as CSCs. And based on this age, they estimate the anthropogenic CO2 in the water parcel, knowing the history of the concentration of anthropogenic CO2 in the atmosphere. In my PhD study, we estimated the anthropogenic CO2 in the ocean using the physicity zero method, which has been previously applied in the whole Atlantic Ocean, and gave inventory estimates which are in good agreement with the other methods. So, although ocean acidification occurs in the world ocean, it presents marked regional differences. As you can see in the plot, half of the concentration of the anthropogenic CO2 is stored in the 400 first meters of the ocean. And the deep penetration of the anthropogenic CO2 depends on the slow vertical mixing of the water column and of the movements on the transports of the water masses. However, in regions where the vertical movements are relatively fast, such as the North Atlantic Ocean, the deep penetration of anthropogenic CO2 into the deep ocean is in order of decades instead of centuries, and therefore these regions are faster exposed to the anthropogenic acidification. This is the reason why we decided to study the subpolar North Atlantic region in this thesis. The subpolar North Atlantic region plays an active role in the regulation of the European climate and in the absorption and transport of CO2 into the ocean interior through the meridional overturning circulation. In a very simplistic manner, the meridional overturning circulation carries warm and salty waters from the subtropics to high latitudes in the North Atlantic, and during this transport, these waters become denser by cooling and sink, process known as water mass formation, and then they return southwards as deep and bottom waters. During this transport, the sequestration of CO2 occurred during this transport maintains the capacity of the North Atlantic Ocean to restore to uptake anthropogenic CO2. And in fact, the North Atlantic Ocean stores about 25% of the total anthropogenic CO2 stored in the oceans, despite being only 15% of the global ocean area. For all these reasons we exposed, we decided to focus on accomplish three main goals in this thesis. The first one is to determine the water mass distribution, transports, and transformations in the subpolar North Atlantic. The second one is to evaluate the trends of the stressors of the seawater CO2 system in the subpolar North Atlantic. And the third one was to evaluate the transport of anthropogenic CO2 and their interannual to decadal variability across the subpolar North Atlantic region. So I'm going to expose the results of the first study in which we accomplished the first goal of my PhD. And in this study, we studied the structure, transports, and transformations of the water masses in the Atlantic subpolar gyre. The concrete goals of this study were to evaluate the distributions of the main water masses in the North Atlantic region for the first decade of the 2000s, to evaluate the interannual variability of the water mass structure from 1997 to 2010, to evaluate the water mass volume transports and their contribution to the Atlantic meridional overturning circulation, and to evaluate the water mass transformation that take place in the North Atlantic region. For these purposes, we used data of 6 repeats of the A25 hydrographic section. The data include the Furex section taken in 1997 and 5 repeats of the Bight section taken every other year from 2002 to 2010. In the figure, you can see the hydrographic station of both lines and a scheme of the North Atlantic circulation. So the distributions of the main water masses in each section were determined using an optimum multiparameter analysis, also known as OMP analysis. An OMP analysis is a simple mathematical approach based on measured data that shows the mixing between water masses. In those analyses, the water masses are represented by the source water types. In our study, we used 14 source water types, and we grouped them in 11 mixing figures, which are groups of source water types that are susceptible to mix together. The goal of an OMP analysis is to find the fractions of each source water type in its water sample. But when evaluating the distributions resulting from an OMP analysis, it should be taken into account that the properties that define the source water type are time invariant, and therefore the changes of the properties of the water masses over time are represented through water mass redistributions. So these are the main water mass distributions for the first decade of the 2000s, resulting from our OMP analysis. The upper waters are represented by the central waters, the subpolar mud water of the Iceland Basin, and the subpolar mud water of the Erminger Basin. The central waters occupy the upper eastern part of the section from the Iberian Peninsula until the Reykjanes Strait. The subpolar mud water of the Iceland Basin presents its main core over the Reykjanes Strait, and this water mass reaches surface in the Erminger Basin, although it is formed in the Iceland Basin, and this indicates us that at the time of the Bight sections, the waters of the surface waters of the Iceland Basin were warmer than 8 degrees, that is the temperatures that we assign to this water mass. And finally, the distribution of this water mass also shows its transport from the Iceland Basin to the Erminger Basin by the Erminger current. That is, the subpolar mode water of the Erminger Basins present its main core over the Greenland slope, from where it extends eastward. And this distribution indicates that the major region of formation of this water mass could be the northwest of the Erminger Basin, from where the East Greenland Erminger current could transport it southwards until the Ovid sections. The intermediate waters are represented by the subarctic intermediate water, the Mediterranean water, and the Labrador Sea water. The distribution of subarctic intermediate water presents a maximum located in the Iceland Basin, which is associated with its advection from the Labrador Sea, and its distribution also shows its subduction beneath the central waters. The Mediterranean water presents its main core of about 1,200 meter depth of the shelf of the Iberian Basin, from where it extends westwards, and its westwards extension could be linked to its transport by Medes and by the Azores countercurrent. The Labrador Sea water is the main water mass of the sections. Its distribution presents two main cores separated by the Reykjanes Ridge, and the gap separating both cores may indicate the strong mixing that happens around the ridge, where the presence of other water masses reduces the presence of Labrador Sea water. We also find high amounts of Labrador Sea water near the Iberian Peninsula. The overflows and deep waters are constituted by the Denmark Strait overflow water, the Iceland-Scotland overflow water, and the polar intermediate water, and the Northeast Atlantic deep water. The Denmark Strait overflow water occupies the deepest part of the Greenland continental slope. The Iceland-Scotland overflow water presents its main core at the eastern flank of the Reykjanes Ridge, from where it extends eastwards. And this eastward extension may indicate that part of this water mass must bypass the Charles fracture zone and flow into the West European Basin. We also find important fractions of Iceland-Scotland overflow water in the interior of the Erminger Basin, associated with its northward advection after crossing the Charles fracture zone. The inclusion of the polar intermediate water in our analysis is an attempt to model the entrainment events of shelf waters into the deep overflows of the Erminger Basin. The distribution of the polar intermediate water, even though in a very narrow area, supports the statement of the existence of certain dynamical processes that link the East Greenland shelf waters with the deep overflows. Finally, the Northeast Atlantic deep water is the dominant water mass in the West European Basin from 3,000 meter depth to the bottom. Now, with respect to the time variability of the water masses between 1997 and 2010, first we evaluated if the different section pathway influences the distributions of the water masses. For this purpose, we used data of the Meteor's cruise that was taken almost at the same time that the Furex section, and which cruise track shares the track of the Ovid section in the Erminger and Iceland basins. In the case of the Labrador Sea water, the section pathway doesn't affect the distribution of this water mass in the Erminger Basin, although it is an important contributor of the variability of this water mass around the Reykjanes Ridge and in the Iceland Basin. We also observe that the contribution of Labrador Sea water gradually decreases over time, being this decrease faster in the Erminger Basin than in the Iceland and West European basins. In the case of the subpolar mode water, we also observe that the section pathway is an important component of the variability of this water mass. If we look at the both distributions taken in 1997, we observe that at the Furex section we have lower amounts of subpolar mode water than the Meteor section. And this may be explained by the fact that the main path of the North Atlantic current around the Reykjanes Ridge turns before arriving to the Furex section, thus resulting in lower amounts of subpolar mode water arriving to the Furex section. For the same section location, we observe that the importance of the subpolar mode water increases over time, being this increase linked to the different properties of the water masses and their formation regions. Concretely, for the Erminger Basin, this increase may be linked to the reduction in the deep convection in the Labrador Sea, which resulted in a shallower variety of Labrador Sea water, which our model represents by adding more subpolar mode water. In the case of the Iceland-Scotland overflow water, we also observe that the section pathway is an important component of the contribution of the variability of the distributions of this water mass. For the food section, we observe that the percentages of the core located at the eastern flank of the Rehannes Ridge fall below 70%, whereas for the meteor section, this core presents percentages greater than 80%. And this may be explained by the existence of a flow of part of this water mass through gaps north of the Charlie Gibbs fracture zone, in between both section lines. That makes that lower amounts of Iceland-Scotland overflow water arrive to the Furex section. And we also observe differences in the distribution of this water mass in the Erminger Basin. And these differences may be explained by the distance of both lines to the fracture zone. The closer distance, the closer Furex section presents higher percentages of Iceland-Scotland overflow water in the Erminger Basin, although the great distance between the fracture zone and the meteor section makes that the Iceland-Scotland overflow water arrives more diluted to that section. For the same section location, we observe that the importance of Iceland-Scotland overflow water in the Erminger Basin increases over time, being the greatest change between 1997 and 2002. We attribute this variability to the fact that the concentration of Labrador seawater in the Erminger Basin is decreasing over time, thus leaving more space to the Iceland-Scotland overflow water to enter the basin. In the case of the demarcated state overflow water, it seems to be colder at the Furex location than at the meteor location, which is represented by higher percentages of demarcated state overflow water, which is represented in color, and higher of polar intermediate water, which limit is marked by the white dashed line. For the same section location, the distribution of the demarcated state overflow water presents no apparent trend at interannual time scales. However, in 2002 and 2004, the presence of polar intermediate water is greater than in the other years, and this is in agreement with the entrainment events observed in previous works. Now, by combining the water mass structure resulting from the OMP analysis with the velocity fields of the section, we obtain the water mass volume transports across the sections. In these figures are represented the mean water mass transport from the period between 2002 and 2010, and the transports were calculated perpendicular to the sections, being positive when being northwards. In our recent study, Mercier et al. Estimated the magnitude of the upper and lower limbs of the meridional overturning circulation, and considering the isopygnal that separates both limbs in that study that was performed in the same sections that we use, we assign its water mass to each one of the limbs of the meridional overturning circulation. So the upper limb of the meridional overturning circulation in our study is composed of central water, subpolar mud water of the Iceland Basin, subarctic intermediate water, and Mediterranean water, and the lower limb is composed of subpolar mud water of the Erminger Basin, Labrador seawater, Northeast Atlantic deep water, polar intermediate water, Iceland-Scotland overflow water, and Denmark Strait overflow water. Although the water masses that are assigned to each limb of the meridional overturning circulation in our study may overlap both limbs, the results of our approach are in good agreement with those of the study of Mercier et al. By performing the same methodology with the Furex section, it is by combining the results of the OMP with the velocity fields of the section, we obtain the water mass transports and the magnitudes of the upper and lower limbs of the meridional overturning circulation for the year 1997. The decrease of the magnitude of the meridional overturning circulation between 1997 and the 2000s may be linked to the reduce of the transports of central water, subpolar mud water of the Erminger Basin, and polar intermediate water. Finally, taking advantage of the estimated water mass volume transports, we infer the circulation and transformations that take place in the North Atlantic subpolar gyre. We study these transformations by a two-layer box model in between the Obaid section and the Greenland, Iceland, Scotland section. Not section. And the boundary between the eastern and western basins is the Rehannes Ridge, which is open for the upper boxes and closed for the lower boxes. The final four boxes were obtained by dividing vertically both basins by the isopygnal 36.94, which is traditionally the upper bound of the deep waters. In order to obtain the volume batches of the boxes, for the northern boundary we consider the volumes transport available in literature, which are represented in gray, and for the southern boundary we use the water mass transports estimated in our study. The net volume transport in the Erminger Basin result in a deficit of 9.5 spare drops, and in an excess of 9.4 spare drops in the East North Atlantic Basin. Therefore, 9.4 spheres should flow from the East North Atlantic Basin to the Erminger Basin over the Reykjane Strait. Doing the same for its basin, we obtain an excess of 1.7 spheres in the lower East North Atlantic box and a deficit of 1.7 spheres for the upper East North Atlantic box. Therefore, these 1.7 spheres should upwell from the lower to the upper East North Atlantic boxes. And the same for the Erminger Basin, we obtain a deficit of 3.4 spheres for the lower Erminger box and an excess of 3.5 spheres for the upper Erminger box. Therefore, this excess of 3.5 spheres should downwell and become part of the lower Erminger box. So taking advantage of our water mass distributions, we can know the composition of all these volume fluxes volume flows. So for the 1.7 spheres upwelling from the lower to the upper East North Atlantic boxes, we infer that the composition of these flows would be the Iceland-Scotland overflow water, since from the 3 spheres entering the basin across the Iceland-Scotland seals, only 1.4 spheres leave the basin. Therefore, we have an excess of 1.6 spheres in this box that should be upwell and become part of the upper East North Atlantic box. This upwelling is corroborated by the software transport of this water mass in the upper East North Atlantic box. But not all the water mass that has upwell exits the box, so the excess should flow over the ridge and become part of the Erminger Basin, which is corroborated by the net software export of this water mass in the Erminger Basin. To know the composition of the rest of the components of the 9.4 spheres flowing from the East North Atlantic Basin to the Erminger Basin, first we should know the composition of the 7 spheres leaving the East North Atlantic Basin across the Iceland-Scotland seals. From literature, we know that this flow presents temperatures greater than 7 degrees. Therefore, only the central waters, the Mediterranean water, and the subpolar mud water of the Iceland basins are possible sources for this flow. However, we know that the subpolar mud water is formed in the Iceland basin near the Reykjane Strait, and it cannot flow northwards and leave the basin. Considering that 11.8 spheres of central waters and Mediterranean water enter the upper East North Atlantic box across the bight section, and then 7 spheres should flow northwards and leave the basin, we obtain that we have 4.8 spheres available to cross over the ridge. We know that the Mediterranean water flows northward across the Rockall Throw and doesn't reach the Reykjane Strait. Therefore, these 4.8 spheres are all attributed to the central waters. We also know that when the central waters arrive to the Iceland basin, 2.7 spheres are transformed into subpolar mud water of the Iceland basin, thus leaving 2.1 spheres of central waters available to cross over the ridge. The rest of the flow crossing over the ridge is constituted by the waters colder than 7 degrees entering the upper East North Atlantic box, and which are 4 spheres of subarctic intermediate water, 2.4 spheres of Labrador sea water, and the 0.9 spheres of Iceland-Scotland overflow water previously estimated. Now for the 3.5 spheres downwelling from the upper to the lower Erminger box, we infer that the Labrador sea water and the Iceland-Scotland overflow water must be the major contributors of this flow. And in fact, the flows of both water masses in the Erminger basin are almost compensated by their corresponding flows over the Reykjane Strait. Finally, our results also give insights about the water mass transformation that take place in the North Atlantic subpolar gyre. In the upper East Erminger box, we have an excess of 2.1 spheres of central waters. Besides, for the 4 spheres entering the Erminger basin, only 1.8 spheres leave the basin across the bight section, thus leaving an excess of 2.2 spheres of subarctic intermediate water in the Erminger basin. Considering that 1 sphere of Atlantic waters leave the basin across the Greenland-Iceland seals, we obtain an excess of 3.2 spheres of central waters and subarctic intermediate water for the upper Erminger box. On the other hand, considering that the subpolar mud water of the Erminger basin derives from the subpolar mud water of the Iceland basin, and that the inputs from the latter in the Erminger basin only account for 5.3 spheres, we obtain a deficit of 3.5 spheres of subpolar mud water in the Erminger basin. Therefore, the 3.2 spheres of central water and subarctic intermediate water should have contributed to the volume transport of the subpolar mud water of the Erminger basin. Now I am going to present the results of the second study that we performed to achieve the second goal of my PhD, in this study we describe and discuss the observed trends of the stressors of the CO2 system in the Erminger and Iceland basins. The concrete goals of this study were to give a detailed description of the stresses of the CO2 system in the water masses of the Erminger and Iceland basins for the last 3 decades, concretely from the period from 1991 to 2014, based on direct observations. We studied the changes of total alkalinity, anthropogenic CO2, pH, and saturation states of aragonite. And the second concrete objective was to infer the future changes in pH and saturation states of aragonite for the end of the century based on the observed trends for the period study. For these purposes, we selected data of 12 cruises along the same cruise track across the Erminger and Iceland basin with the cruise dates spanning over 33 years, from 1981 to 2014. During these cruises, measurements of pH, total alkalinity, and total dissolved inorganic carbon were performed, and based on those measurements, we estimated the concentration of anthropogenic CO2 and the saturation states of aragonite. To estimate how much of the change in pH is due to the uptake of anthropogenic CO2, the pH values were decomposed into the pH change due to the uptake of anthropogenic CO2 and the pH not directly related to the uptake of anthropogenic CO2. To compute both terms, first we estimated the natural total dissolved inorganic carbon of the sample. It is the total dissolved inorganic carbon of the sample that the sample should have without the presence of anthropogenic carbon. Then the non-anthropogenic term was computed using this natural total dissolved inorganic carbon. And finally, the anthropogenic term was calculated by subtracting the non-anthropogenic component to the measured pH. The changes in the variables of the seawater CO2 system were determined for the main water masses sampled in the Erminger and Iceland basins. We used this water mass methodology to keep to a minimum the variability of the properties within its layer. In the figure I represented the limits of the water masses and the basins you considered in this study, plotted on the mean salinity of the section. Now I'm going to present the results of the study, starting with the alkalinity. On the lower panel, you can see that the waters of the Erminger and Iceland basin present an almost homogeneous value of alkalinity. However, in the Iceland basin, the subpolar mud water and the Iceland column overflow water present higher values of alkalinity. The high values of alkalinity of the Iceland column overflow water are related to the influence on the lower North Atlantic deep water. And the high alkalinity values of the subpolar mud water are due to the high salinity of this water mass. On the top panels are represented the long-term evolution of the mean values of the salinity normalized total alkalinity. We normalize the alkalinity values to a salinity of 35 to eliminate the influence of salinity to the alkalinity. The classical Labrador seawater represented in black, the Iceland column overflow water represented in green, and the Denmark Strait overflow water represented in pink present a significant long-term trends of increase in alkalinity in the Erminger basin, which can be related to the increasing arrival of Arctic waters to the Erminger basin. In response to the increasing anthropogenic CO2 in the atmosphere, the waters from both the Erminger and Iceland basins are gaining anthropogenic CO2. On the top panels, you can see that the subpolar mud water represented in red presents the greatest rate of increase of anthropogenic CO2 due to its direct contact with the atmosphere. In the Erminger basin, anthropogenic CO2 levels of the subpolar mud water keeps rising at about 85% of the expected rate if we assume saturation with the atmospheric CO2. And we explain this by the fact that the surface seawaters reach the equilibrium with the atmospheric CO2 levels within a period of about 5 years. However, in the Iceland basins, the CO2 levels of anthropogenic CO2 of the subpolar mud water keep rising at about 64% of the expected rate since saturation with the atmosphere is assumed. And we explain this by the thicker subpolar mud water of the Iceland basin, which includes poorly ventilated waters with low content on the anthropogenic CO2. We don't observe any change in the rates related to the change in the NAO index, and we explain this by the fact that the increasing amounts of anthropogenic CO2 in the atmosphere counteract the effect of the NAO index. The upper Labrador seawater represented in blue and the classical Labrador seawater represented in black present a similar pattern in the evolution of the CO2 values in both basins. However, the rates in the Erminger basins are greater than that of the Iceland basin due to the younger waters present in the Erminger basin. From 2006 onwards, in the Erminger basin, the upper Labrador seawater gains anthropogenic CO2 faster than the classical Labrador seawater, being its tendency more similar to that of the subpolar mud water. And we explain this by the enhancement of the formation of upper Labrador seawater due to the change of the NAO index between the mid-1990s and the 2000s. The classical Labrador seawater in the Erminger basin gains anthropogenic CO2 rapidly from 1991 to 1997, where it has its maximum concentrations. From 1997 to 2002, this water mass loses anthropogenic CO2, and then it gains again anthropogenic CO2 from 2002 to 2010, although at a lower rate than that observed between 1991 and 1997. And we link all these changes to the changes in the NAO, to the changes in the circulations related to the changes in the NAO index. The Iceland Scotland overflow water, represented in green, presents a continuous increase in the concentration of anthropogenic CO2, being the mean values greater in the Erminger basin than in the Iceland basin, and this is related to the fact that the signal of the Iceland Scotland overflow water is diluted in the Iceland basin by the signal of the lower North Atlantic deep water. In the Erminger basin, the Denmark Strait overflow water presents a similar pattern of increase in anthropogenic CO2 concentration that observed in the Iceland Scotland overflow water, which may be related to the strong mixing between both water masses, but it also indicates that these two water masses have a common origin that in last instance track the increasing amounts of anthropogenic CO2 in their Arctic source waters. Now for the pH, on the lower panel is represented the mean pH of the section, which presents higher pH values in the near surface waters, which rapidly decreases with increasing depth. And as I explained in the introductory section, the net effect of the absorption of CO2 by the ocean is a decrease in the pH, and the seawater pH, and this decrease is observed in the upper panels in all the layers of both basins, being these rates greater in the Erminger basin than in the Iceland basin due to the younger waters present in the Erminger basin. The general pattern is a decrease of the acidification trends with increasing depth, with being the layers of the Denmark Strait overflow water presenting a similar pattern of that of the subpolar mud water on surface, which indicates that this water mass has been recently in contact with the atmosphere. The decomposition of pH into the anthropogenic and non-anthropogenic components allows inferring the possible causes of the pH changes that we observe. I'm only going to explain the trends that have a significant trend for the non-anthropogenic component. In the case of the subpolar mud water, we observe that the pH change observed for the studied period is only 72% of the expected change if we assume the change due to the anthropogenic component. And this is explained by the buffering effect of the non-anthropogenic component, which is caused by the arrival of salty and alkaline subtropical waters to the sections transported by the North Atlantic current. In the case of the classical Labrador seawater in the Erminger basin, its acidification trends are 34% higher than the acidification directly related to the uptake of anthropogenic CO2, and we explain this by the contribution of the non-anthropogenic term related to the aging of this water mass. Regarding the saturation state of calcium carbonate, on the lower panel you can see the mean saturation of aragonite for the section, and you can see that the surface and intermediate waters are saturated in aragonite, which is represented by a saturation state over 1, and the waters below 2500 meters depth are unsaturated in aragonite. On the top panels are represented the long-term evolution of the mean values of the saturation state of aragonite for the Erminger and Iceland basins. And if we exclude the data of 1997, which is an outlier, we observe that all all the layers in both basins present a significant decrease in trends in the saturation state of aragonite, being the greatest change observed in the upper Labrador seawater. The decrease in trends observed in the intermediate waters corresponds with a swelling of the saturation horizon of about 10 meters per year. So, taking advantage of the observed changes in pH and saturation states of aragonite for the period between 1991 and 2014, we infer the future changes of these variables. So, according to our estimates, when the atmospheric CO2 reaches 800 ppm, which is about twice the present atmospheric CO2 concentration, the pH of subpolar mud water could drop off by about 0.31 pH units with respect to the pre-industrial value, which is in agreement with the predictions of the worst scenario of the IPCC. And a similar pH decrease is projected for the Denmark Strait overflow water. According to our observations, to our predictions, we also can conclude that when the atmospheric CO2 reaches 800 ppm, the whole water column of the Ermingarden Island basin will be undersaturated in aragonite. However, the upper and classical Labrador seawater would reach undersaturation faster, and this early undersaturation may affect negatively the cold water corals that inhabit the depths at which these water masses are located. Now, finally, I'm going to expose the results of the third study, in which we study the variability of the transport of anthropogenic CO2 at the Greenland to Portugal Divide section, with a special focus on the controlling mechanisms. The concrete objectives of this study were to analyze the variability of the transport of anthropogenic CO2 in the subpolar North Atlantic at interannual to decadal timescales, to evaluate the effect of the different elements of the ocean circulation on the variability of the transport of anthropogenic CO2, and to analyze the influence of the increase in anthropogenic CO2 in the ocean in the variability of the transport of anthropogenic CO2. For these purposes, we used the data of the A25 hydrographic section taken between 1997 and 2010, like in the first study. And the transport of any properties across the Greenland to Portugal section can be calculated by integrating the product of the property concentration, the velocity orthogonal to the section, and the in situ density from Greenland to Portugal over the entire water column. Usually this integration is performed in pressure coordinates, but due to the horizontal gradient present in the sections and the circulation pattern, it is preferable to do this integration in density coordinates. So the geostrophical transport of any property can be decomposed into three components. The net component represents the transport of anthropogenic CO2 associated with the net water transport of one aspergus associated with the Arctic mass balance. The diapinal component is linked to the diapinal circulation, which accounts for the light to dense water mass transformation related to the meridional overturning circulation. And finally, the isopinal component quantifies the isopinal transport of anthropogenic CO2. It is the integration of how the anthropogenic CO2 and the transport covariate in its layer. Now I'm going to present the results of the study. In the plot are represented in black the transport of anthropogenic CO2 as a function of time, and its components, diapinal in blue, net in green, and isopinal in red. The dashed gray line is the Ekman transport of anthropogenic CO2, which is dispatched between the other three components. Note that the positive values indicate a northward transport of anthropogenic CO2 across the section. The transport of anthropogenic CO2 for the studied period presents a mean value of 254 kmol per second, and its interannual variability with a decrease between 1997 and the mid-2000s and a recovery thereafter blurs any long-term trend in the transport of anthropogenic CO2. Regarding each one of the components, the mean values for the studied periods are a northward transport of 400 kmol per second for the diapinal component, a northward transport of 26 kmol per second for the net component, and a southward transport of 171 kmol per second for the isopinal component. Now, I am going to evaluate which elements of the circulations have a major influence of the variability of the transport of anthropogenic CO2 across the studied section. The variability of the transport of anthropogenic CO2 and the variability of the diapinal component are well correlated. By contrast, the variability of the isopinal component is not correlated with the variability of the transport of anthropogenic CO2, and the same occurs between the variability of the net component and the variability of the transport of anthropogenic CO2. Therefore, the diapinal component is the principal driver of the variability of the transport of anthropogenic CO2 across the section. If we decompose the diapinal components in terms of mean profiles of volume and anthropogenic CO2, you observe that the vertical profile of the diapinal component follows perfectly the vertical profile of the anomaly of volume transport. Although the vertical integration of the volume transport is equal to 0, the larger concentration of anthropogenic CO2 in the upper limb of the meridional overturning circulation than in the lower limb results in the higher northward transport of the diapinal component. So in terms of volume transport, the diapinal component is directly related to the meridional overturning circulation. However, during the period of time studied in this work, the intensity of the meridional overturning circulation is not correlated with the transport of anthropogenic CO2, and the same occurs with the diapinal component. This also suggests that although the diapinal circulation is related to the meridional overturning circulation, in the case of the transport of anthropogenic CO2, there is another factor acting on the variability of the diapinal component, which is very likely the different change in the concentration of anthropogenic CO2 between the upper and lower limbs of the meridional overturning circulation. We observe that the difference between the concentration of the upper and lower limbs of the meridional overturning circulation keeps increasing independently of the variability of the meridional overturning circulation at a mean rate of 0.43 micromole per kilo per year. So based on this, we propose an estimator to help to clarify the effect of the circulation changes and the changes in the concentration of anthropogenic CO2 in the transport of anthropogenic CO2 across the section. This estimator is based on the difference between the mean value of anthropogenic CO2 between the upper and lower limbs of the meridional overturning circulation and in the intensity on the meridional overturning circulation computed in density coordinates. It is expected the estimator to be a good approximation of the diapinal component, and in fact, the estimator and the diapinal component are well correlated. And using this estimator, we can infer the relative contribution of at long time scales of the transport of anthropogenic CO2 increase and the circulation to the transport of anthropogenic CO2 across the section. If we assume a steady meridional overturning circulation of 16 spare drops, the transport of anthropogenic CO2 across the section estimated by our estimator increases at a rate of 7 kmol per second per year. It means that the increase in anthropogenic CO2 yields an increase to the northward transport of anthropogenic CO2 across the section. If we take into account the slowdown of 25% of the meridional overturning circulation by the end of the 21st century predicted by models, the transport of anthropogenic CO2 resulting from our estimator also increased, but at a lower rate of 4.3 kmol per second per year. Now I'm going to present the main conclusion of each one of the studies. For the first study, we conclude that the Labrador seawater is the main water mass of the section, representing 35% of the volume of the sections, but its extension is progressively reduced over time. The OMP results reveals that the Labrador seawater is strongly mixed with the surrounding waters at and upstream of the Reyhan Straits and in the deep western boundary current. We also conclude that the waters from the East North Atlantic Basin cross over the Reyhan Straits and enter the Erminger Basin. The flow of 9.4 asperges flowing across the Reyhan Straits is constituted by the central waters, the subarctic intermediate water, the Labrador seawater, and the Iceland-Scotland overflow water. The assessment of the box patches allows disentangle the formation pathway of the subpolar mud water. In the East North Atlantic Basin, the central water contributes to the formation of the subpolar mud water of the Iceland Basin. And in the Erminger Basin, the central water and the subarctic intermediate waters contribute to the formation of the subpolar mud water of the Erminger Basin. The distribution and transport of Iceland-Scotland overflow water allow inferring that in the course of the journey of this water mass from the Iceland-Scotland seas to the Charlie Geese fracture zone, part of it outwells and flows into the Erminger Basin through gaps in the Reyhan Straits. Now I'm going to present the conclusions of the second study. We observed that the increasing atmospheric CO2 concentration has significantly decreased the pH of the whole water column of the Erminger and Iceland basins, with the greatest change observed in the near surface and intermediate waters. Our separation of the pH changes into the anthropogenic and non-anthropogenic components tell us that the subtropical waters transported by the North Atlantic current buffer the acidification caused by the increase in anthropogenic CO2 of the upper layer. And in the Erminger Basin, the acidification of trends of the classical Labrador seawater are reinforced by the aging of this water mass. and that the deep waters of the Erminger Basin present a clear evidence of significant acidification from anthropogenic forcing. Based on our estimates, by the time the atmospheric CO2 reaches 800 ppm, subpolar meltwater would experience a pH drop of about 0.31 pH units with respect to the pre-industrial value, which is in agreement with the predictions with the worst scenario of the IPCC, and similar pH decrease is projected for the Denmark Strait overflow water. According to our estimates, also the addition of anthropogenic CO2 during the last 33 years has caused the Aragonese saturation horizon to swell at a rate of about 10 meters per year, which is more than twice the swelling trend previously found in the Iceland basin. According to our estimates, the whole water column of both basins will be undersaturated in Aragonite by the time the atmospheric CO2 reaches 800 ppm, which is going to be by about 2065. And however, the upper and classical Labrador seawater would reach Aragonite undersaturation faster. The data compiled in this study also show significant long-term trends of increasing alkalinity in the deep waters of the Erminger Basin, which may be related to the increase in the river discharge in the Arctic Ocean. And finally, the conclusions of the last study is that we find a northward transport of anthropogenic CO2 across the section with a mean value for the study period of 254 kmol per second, and no significant long-term changes have been identified due to the interannual variability of the transport of anthropogenic CO2. By splitting the transport of anthropogenic CO2 into its components, we conclude that the diapinal component is the major contributor of the variability and of the transport of anthropogenic CO2, and it also is the main contributor of the transport of anthropogenic CO2 in itself. The estimator is an schematic representation of the diapinal component, and from the application of this estimator, we conclude that the variability of the meridional Albertine circulation dominates the variability of the transport of anthropogenic CO2 at interannual to decadal time scales, but the increase in anthropogenic CO2 seems to control the transport of anthropogenic CO2 at longer time scales. Finally, the difference between the concentration of anthropogenic CO2 in both limbs of the meridional Albertine circulation keeps increasing despite the variability of the meridional Albertine circulation, which is going to cause an increase in the transport of anthropogenic CO2 across the section, despite the predicted slowdown of the meridional Albertine circulation by the end of the century. And this is all. Thank you. Exceeds the regulation capacity of the Earth system feedbacks to restore the system. Therefore, there is a growing concern about how ocean acidification may impact marine organisms, global biogeochemical cycles, and climate. So to know how much of the anthropogenic CO2 has been uptaken by the ocean, we require a method that allows distinguishing the natural and anthropogenic components. But this is a difficult task for a variety of reasons. First, anthropogenic CO2 cannot be distinguished from natural CO2, and it has to be inferred from indirect means. Second, the anthropogenic perturbation represents only about 3% of the total dissolved inorganic carbon in the ocean. And finally, the anthropogenic CO2 presents a distribution that is rather heterogeneous in the ocean. Therefore, several methodologies have been developed to estimate the anthropogenic concentration in the ocean. Fundamentally, these calculations are approached either using bulk calculation methods or using methods based on the measured variability of this term, and there assumes a disequilibrium term that is proportional to the concentration of anthropogenic CO2 in the water masses. The transient tracer-based methods determine the age of a water parcel based on the measurements of transient tracers such as CSCs. And based on this age, they estimate the anthropogenic CO2 in the water parcel, knowing the history of the concentration of anthropogenic CO2 in the atmosphere. In my PhD study, we estimated the anthropogenic CO2 in the ocean using the PCT0 method, which has been previously applied in the whole Atlantic Ocean, and gave inventory estimates which are in good agreement with the other methods. So, although ocean acidification occurs in the world ocean, it presents marked regional differences. As you can see in the plot, half of the concentration of the anthropogenic CO2 is stored in the 400 first meters of the ocean, and the deep penetration is on transient tracers. Back calculation methods try to separate the anthropogenic perturbation based on the premise that the anthropogenic CO2 can be isolated from the measured total dissolved inorganic carbon by subtracting the pre-industrial value and the contribution of the biology. Furthermore, a disequilibrium term is also included to account for the fact that the surface seawaters are rarely in complete equilibrium with the CO2 concentration in the atmosphere. Fundamentally, we can the back calculation methods are the delta C star and the variations thereof, such as the physicity zero methods. There are other methods of back calculation, but these are the main ones. And the main difference between both terms is the treatment of this equilibrium term. And the delta C star methods assumes a disequilibrium term that is constant over time, while the physicity zero method takes into account the temporal limiting the rise in the concentration of atmospheric CO2 and hence the warming related to this greenhouse gas. When CO2 dissolves in seawater, they react and form carbonic acid, which rapidly dissociates into carbonate ions, which in turn can dissociate into bicarbonate ions, which in turn can dissociate into carbonate ions. But dissociation reaction reduces the pH of seawater. In this plot are represented the relative fractions of the seawater carbon species, and in the pH of the modern surface seawaters there is a relatively high proportion of carbonate ions, which is represented in green. But if the pH of the seawater lowers due to the increase in the concentration of CO2, the concentration of carbonate ions will decrease, and this may affect marine calcifying organisms like Coccolithophora, foraminifera, and corals. Recent studies show that the present uptake of anthropogenic CO2 and the subsequent acidification is about 100 times faster than during the last ice age. And this rate far. Good morning, my name is Maribel and I'm going to present the results of my PhD entitled Acidification and Transports of Water Masses and CO2 in the North Atlantic. This thesis has been supervised by Dr. Fitz Fernandez Perez. It's not working, okay. So I'm going to start by giving a general introduction about the CO2 cycle and the importance of the North Atlantic in that cycle. Then I'm going to expose the main goals of my PhD and the results of the studies performed to achieve those goals. And then I'm going to expose the main conclusions of those studies. So a small portion of the Earth's atmosphere is composed of greenhouse gases that absorb and contain infrared radiation, which warms the Earth's surface and atmosphere. Since the Industrial Revolution, anthropogenic activities have been gradually increasing the CO2 concentration in the atmosphere, but not all this CO2 has remained in the atmosphere. Part of it has been absorbed by the ocean and land, thus